time, I don't want to go through every detail here. The mu's represent the fixed points of this map, so mu0 is the origin. There's a mu1 right here, a mu2, and a mu3. And you can see by the shape I've graphed y equals x, and the function f, the extension I talked about. And this function is invariant on the interval from mu1 to mu3. You can see that from the shape of the curve. And there are some interesting things that happen. Almost every point in that interval iterates to one of those two cycles I mentioned. Mu3 is what we call a snapback repeller. That is, if I start just barely above there, I can always pick some points that run away, do whatever, but then they run back and they land on mu3 exactly. There exists a non-integer monotone divergent orbit. That is, I can find some starting point so that it will go up and up and up, and it will run away to infinity in a monotonic fashion. So all this suggests that there is some chaotic behavior going on with this map. And indeed, I could show not just for my extension, but for any extension of the map T, there will be these things, a snapback repeller. There will actually be a whole Cantor set of divergent trajectories, and there will be periodic orbits of every period. So there's some kind of chaotic dynamics going on with any map, which suggests to me that might explain, with some perspective, why this problem is so complicated. There are really some kind of chaotic dynamics going on underneath, and that could explain, at least partly, why this problem is so difficult to solve. And this is an associated, Julia said, if I extended my function to the complex plane, not just the reals, you get kind of these Mandelbrot-looking type things coming out. All right, here's a different characterization of the 3x plus 1 problem. You start with this functional equation. Looks kind of a bit complicated, but and omega is a cube root of unity. And the claim is, if you can show that the only power series solution where I'm restricting a sub n to be either zeros or ones, the only power series solution to this is the trivial solution, that will prove the 3x plus 1 problem. That's also not too difficult to show. It's an interesting exercise, but it's not obvious just by looking at the functional equation. Okay, so again, we've looked at the idea of extending the space of the problem. Also another approach people do, if you can't solve the original problem, try to generalize the problem and see if you can see some general structure. So Keith Matthews, who's an Australian number theorist, who I think I can communicate, he has said he's more or less given up on the problem too. He was looking at similar kinds of maps like this, or like this, and also noticing some very interesting behavior, just like we see for the 3x plus 1 problem. He's offered some prize money for conjectures related.
So these are proven or conjecture?
Conjectures.
Oh, it's still conjecture.
Yeah.
Is
So,
there any similar looking proof? No.
Not for, there are some, and I won't talk about them today, there are some maps which pretend to be of the same spirit, but they're not. They will use floor functions and things like that, and one can get some hard results on those, but it's cheating. They're not really in the same spirit of the functions we're talking about. So let me just mention one, a broader class one can look at. Instead of 3x plus 1, what if I look at the so-called qx plus r problems? So this is playing the role of 3, and this is playing the role of 1. So q and r will be some odd positive numbers. So work on this kind of stuff, trying to generalize it, suggests that if q is 3, no matter what the r is, that everything will converge. There will be a finite number of cycles, and everything will converge to one of those cycles. But of course, that hasn't been proved. And the conjecture is if q is greater than or equal to 5, no matter what the r is, you have to have some divergent trajectory, some starting point that runs away. And again, it's kind of a heuristic argument that works here. If you have a 5 or bigger, just when you hit those odd terms, it just grows so much you can't box it in, you can't control it. The heuristics will say you will be forced to go up on average. And so something should be running away to infinity. And there are more particular results or claims like with V for if numbers and so on. But I just want to give you a little taste there. And then the most general, the maps I was showing in the last term. So now instead of just a branch function with 2 pieces, you can have multiple branches like this as long as things work out nicely with the modulo class. And I've got this D on the bottom, and in our case, D was equal to 2 because we had x over 2 or 3x plus 1 by 2. And depending on what this number works out to be, there are different claims about the stopping time, whether you get nice stuff or not. So there are a bunch of different generalizations, but I don't think this is very helpful. I think we need to focus on the original problem and see what comes out. This was just a curiosity that I'll just mention. This is kind of an aside. This says, suppose m iterates of t apply to the starting point 2a is equal to b. Then this equation is satisfied for some positive integer m if you've got these other guys that satisfy this big congruence. These are all these binomial product of binomial coefficients has to be odd. And this is due to Matusevich, so some serious work is going on here. And I don't know anybody who's tried to do anything with this. But you want to take b equal to 1, and then given an a, see if there exists stuff. But I think this is a very difficult approach. All right, I want to talk about something I've been working on for 1 or 2 years. So I've basically given up on the problem. I started looking at this in the mid-90s. I got my paper before. I wrote a survey article about it about 10 years ago. And then I more or less kind of gave up. And then I got an idea, and I started exploring it. So I just want to talk a little bit about this, and this is something I've more or less written up, and I'm ready to submit. So we're going to build generating functions which encode the dynamics here. So, for example, if I take n to be 0, if I haven't applied t at all to the number k, then we just have this function. If I apply it once, so t applied to 1, 1 maps to 2 under the t map, t maps to 1, 3 maps to 5, 4 maps to 2, etc. And see how I'm just putting the next iterates in the t sequence in. So I'm building this sequence of generating functions, and if we can understand some stuff about these generating functions, that would hopefully shed light on the dynamics of our 3x plus 1 map. Of course, we expect, as n goes to infinity, we expect all of these things to approach a 1. And so eventually, they should all, when you start looking at the low terms here, you're expecting them all to be equal either 1 or 2 for any given value of n. And you see it here. I've already got a 2 and a 1. After one more step, that'll be a 2. There's a 2 and a 2 and so on. The challenge is the lower terms are nice, but the tail is still kind of going crazy. And so the tail is flattening out in the long term, but it's still always there. So can we get some control on it? So first, it's not hard to show that each of these fn's are actually rational functions. Each of those infinite series you can write as a rational function. More specifically, the poles of these rational functions are you have 2 to the n of them, roots of unity. So when n equals 3, the third of these, this guy down here, it's a rational function. And the poles are exactly at these 8 points, the roots of unity. But here was the thing that got me really excited, because I started looking at these functions experimentally, and I found that, so here is the case with n equals 3. I've got these eight poles. If I go to the next step with n equals 4, I will not only have these 8 poles, I'll have 8 new ones, exactly halfway in between. But if you look at the residues at the original 8, the residues are invariant. They don't change. And if I keep iterating more and more, the residues still stay constant. And this is a structure, type of structure, that nobody was seeing in the 3x+1 problem before. So there's some kind of stuff going on here related to this. I'll say that this is, if I put a plus here to represent the 3x+1 map, and I put a minus to represent the 3x-1 map, there's this equality between these two very different generating functions. It's like saying the generating function at 0 for 3x+1 corresponds to the 3x-1 function at infinity. So again, and this is something which has not been seen, there's this interesting connection between these two different problems, which I'm still trying to hammer out some more. So this invariance of the residues got me looking at something more fundamental. So I define these two quantities. First I need to define this ONJ is the number of odd terms in the first n iterates of j. And I know this is a lot to kind of algebraically to take in one moment, but I just want to point out some structure that's going on. Motivated by what I saw with the residues, I ended up defining these two different expressions, the so-called BNs, and the more complicated things, these so-called ANs. And what I was finding is, at these, if you have a root of unity, like one of these guys here, it ends up that the A's and the B's don't change as you go up. This is, one can use this to prove the invariance of the residues, but I can prove these just by doing a lot of complicated algebra without using any of the 3x+1 dynamics. So it allows me to rewrite my generating functions in a closed finite form. I already said they were rational functions, but I have a very explicit form for what they look like, and I have these kind of invariance properties I know about the A's and the B's. So this is a pretty nice form, and I'm trying to get more handle on this. My hope is that I can use some tools from complex analysis, like Montel's theorem and so on, and I'd like to show that I have local boundedness of this sequence of rational functions in the unit disk. If I can do that, I can get uniform convergence, and that, I believe, will tell me I cannot have divergent trajectories for the 3x+1 problem. But this still needs a lot more work, and I'm trying to exploit the structure which I've got here for these generating functions. But there's new structure here, which hasn't been seen before. And my feeling is this is perhaps the most promising way to date. In 1999, I helped co-organize a short 2-day conference on the 3x+1 problem in Germany. So there's a rogues gallery of frustrated people who could not solve, there's me, people who could not solve the problem. And as a reference, in 2010, the AMS published this book. It's a very nice book, very, very readable. Jeff Ligarius was the editor, and he's the acknowledged world expert on the 3x+1 problem. He wrote a couple nice pieces, kind of overview pieces of the whole problem, but we also have some historical articles in there. There are some surveys. I wrote one of the surveys. And for many years now, Jeff has built up an annotated bibliography, so every paper he could get his hands on, he would look at it and do a review of it. And so this has been very invaluable for people who've worked on the problem as well. It's both fun and very frustrating, but I hope you've appreciated the talk. Thank you very much.
Any questions?
Yeah.
Yeah, for the 3x-1 problem, you get cycles, right?
Right.
So what's the difference? Is there any heuristic argument, anything not, of course, not rigorous or anything. Anything that will enable you to tell, oh, sure, for 3x minus 1 we should expect cycles, but for 3x plus 1 we shouldn't. What's the big difference between the two?
Well, here's the crudest way to do a heuristic is to say, if I'm at some point, if I have a 50-50 chance whether it's even or odd, well, if it's even, I'm going to basically scale it by a half. And if it's odd, except for the plus 1 part, I'm basically scaling it by 3 halves. And if you take the multiplicative average, you get something less than 1. So it's saying, on average, I'm going down. And but if you replace this with a 5, then on average you're going up. So that's why I said in these cases the heuristics suggest that there has to be a divergent trajectory.
First of all, that argument doesn't distinguish between 3x minus 1 and 3x plus 1.
Right.
And second, if anything, it makes it seem that 3x minus 1 has an even better chance of going down to 1.
So the heuristic will say that on average, if you start high enough, if you've been iterating enough, you're going to be coming down. So if you can show that everything has to come below a certain threshold, then that means everything else has to eventually enter some cycle. So that's why there's this conjecture that if you have Q equals 3, no matter what the R is, that you have to have a finite number of cycles and you will hit one of those eventually. That's the heuristic. Yes?
So the title that Jeff wrote, The Ultimate Challenge.
All right, I'll just say that wasn't his.
Someone wrote that.
That was somebody at the AMS who said we need to spice this up a little bit. And Jeff told me he wasn't crazy about it, but he wrote in a preface that he accepted this because it's not ultimate as if it's the most important problem, but it's ultimate in the sense that it has the biggest gap between apparent hardness and simplicity of statement. So he can live with that definition of ultimate, and then we're okay. Yeah.
But would it imply, I mean, suppose that we did prove it, I'm sure the proof would be interesting, but knowing the result, does it imply other results other than just for similar types of dynamical systems, or?
Well, Jeff Ligarius has written about that a bit, and his argument is, so there are several components going on, but this is a deterministic problem. We've gotten insight by looking at it as a stochastic problem. And so there's the idea of mixing, and ergodic theorists would be interested in this idea of mixing, and this is it's a toy problem suggesting something higher up may be connected to the idea of mixing that can come up in physics and so on. But as far as are there other big problems that if we knew this one or how to solve this or problems like it, it would imply some other big stuff? No, I don't know that.
But the techniques that may be developed might be used for that.
Perhaps, that's right. But it's more this idea of mixing and the connection between deterministic versus randomness in problems. This problem seems to capture that. I mean, usually if you have randomness, you want to approximate a random process or a stochastic process with a deterministic one. In this problem, we're getting insight by going the other way around, which is somewhat surprising.
Not really.
No?
You know, a lot of discrete problems are approximated by continuous analogs that are much better behaved.
Right, but that doesn't seem to be happening in this problem.
So what were the ideas behind the density result that you're not too impressed by, that you mentioned at the beginning?
Well, I did say I think they're actually probably the strongest results, but there's still infinitely many holes left, and so and that's where the strange stuff can happen. That's related also to the residue results I talk about. So if you can show increasingly smaller or less dense sets are sufficient to prove the whole thing, that would be good enough. But those I feel are kind of the strongest partial results right now, but it's still there's still so much room left over. So it's still not good enough to say if I pick this one big large number to know what its dynamics will be. It's just this general density result, but it's not any more specific than that. So if I start with some huge number, yeah, you can put that number in a computer and wait to see, and it always comes down to 1. And we have rough ideas of even the number of steps it needs to get to 1. But even it's like transcendental numbers. Almost every number is transcendental, but except for some very artificial numbers, we can't point to a nice naturally occurring number and say it's transcendental. So to me it's someone like that here. Almost every number in this density sense iterates to 1, but if you give me one big number, I can't tell you just by looking at it whether it will iterate to 1 or not. So I find that vexing.
It will, because the conjecture is true.
Well, I know you believe that, Doron. So I do too.
Can you go back to the slide on 3x plus 1 dynamics, generating 3x plus 1 dynamics, the first one? Yes, is that forward?
Forward?
Yes, this one.
Generalizing.
Right. I don't understand the second map because you're not dividing by anything. It seems like it's always going up for.
Well, this is going up, but here I'm dividing by 3 in both of these residue classes.
So say n is 3, then you're always going up.
Let's see. So and you're right, in that case you're always going up, and what does it say? It converges to 1. Oh, I must have a typo. I'm sorry. This guy gets a prize. Sorry about that.
And thank the speaker again.